All right, so our next lesson here, to continue perfectly from our last lesson where we solved exponential equations graphically using technology. We are now going to start to do it over the next two lessons. We're going to be doing it algebraically. Okay, and so I showed you the technology portion of it first because I think it gives you a good visualization of what it means to solve two exponential equations. You're looking for the point of intersection, which is a common point between the two curves. Okay, so let's get right into this. I will do all of these examples here with you. And again, we're going to start, these are all would be considered more simple examples. We are going to learn how to solve absolutely any exponential equations in the next lesson where we learn about logarithms, okay? But for this lesson, the examples that are given to us are a little bit easier to do by hand without having any knowledge of what we're going to be learning in the next lesson. All right. And so there is a rule, which it makes absolutely perfect sense, that you can use algebra to determine an exact solution for an exponential equation when the powers on each side of the equations have the same base, which makes perfect sense. Okay, so if you have the same base, so an a and an a on either side of the equation, okay, so let's say a 3 and a 3, that means their exponents have to be equal to each other in order for them to be equal. Okay, so for example, if I had a very basic example, 3 to the power of x is equal to 3 to the power of 2, and I asked you, solve for x here, determine what x must be. Okay, well, you're finding the x value that makes the left side equal to the right side. Okay, and so just by looking at that, what do you think the x needs to be for left side to equal right side? Hopefully you've come to the answer of 2 there. Okay, so of course you have to have 3 squared and 3 squared on either side for them to be equal, which means that x must equal 2 in this case to make them equal to each other. Okay, but let's get to a more complicated example. All right, so we have 4 to the power of 3x plus 1 equals 4 to the power of negative 11. My first question is, do we have a common base? The answer is yes. So now all we need to do is set the exponents equal to each other and solve for x. Okay, because the exponents have to now equal each other. They have to. You got the bases the same. All you need now is the exponents to equal each other, and you will have left side equals right side, or have this equation solved. Okay, so because they're the same base, right, I'm good to just let the exponents equal each other and then solve for x in our exponent. So start by bringing the plus 1 over, becomes minus 1. Okay. Next, divide by 3 on both sides. That cancels out these 3's, and you're left with negative 12 divided by 3, which is negative 4. So our solution there is negative 4. Now you can check your answer, so I'll explain to you how to check your answer. I'm not going to check it every time, but it is important that you know how to check your answer. If x equals negative 4, if I now substitute x into my original equation, I should get identical answers left and right side. So let's try that, okay? So right side, left side. I know my right side is 4 to the power of negative 11. Let's see if I can get 4 to the power of negative 11 on the left if I substitute negative 4 for x. Three times negative 4 is negative 12 plus 1, which is in fact 4 to the power of negative 11. So you can see it checks out. Left side does equal right side. that means I found the proper solution of x. All right, it's x equals -4. But look at the next problem. You don't see the same base there, correct? But we can change 81 to be the same base as a 3. Here's what I mean. We've got to have the same base if we're going to let the exponents equal each other. 81 clearly is not the same as a 3, but I know that 3 to the power of something equals 81. And so you'd pull out your calculator now and you try, okay, 3 squared, no. 3 cubed, no. 3 to the power of 4, jackpot. That equals 81. So I can convert 81 to just appear to be 3 to the power of 4, but I know they're equivalent, but I've manipulated this in a way where I now have the same base. Because I have the same base, I can simply set the exponents equal to each other. Okay, and then try to solve for x. There it is. X equals 2. I'll do another check on this, left side, right side. Okay, so 3 to the power of 2 times 2, because our x is 2 there. I just subbed in 2 for x right there. And then I have 81 on the right side. Here now I have 3 to the power of 4, which is 81. Okay, so both sides equal 81. That means I found the correct x value. Okay, now we get a little bit more challenging, and this is going to test out your knowledge of the exponent laws. So clearly I don't have the same base again, but I have a base of 5 on the left and I have 1 over 125 on the right. I have to change the 1 over 125 to have a base of 5. Let's see here. Well, I know that 125 I can convert to 5 cubed. 5 times 5 times 5 is 125. Okay? Still though, this isn't good enough. I can't have a 5 on the left and a 1 over 5 cubed on the right. But I know from my exponent laws that I can do the following. Bring my 5 to the numerator. And what do I do to the exponent? Flip the sign. So 5 to the -3 is the same as 1 over 5 cubed. Now I have the same base. And I can now set the exponents equal to each other. And then solve for x. Bring the -1 over, becomes +1. Divide both sides by 2. You get -2 divided by 2. And you get x equal to -1. Okay? So you can do a left side, right side check there, okay? But take my word for it on this time, just to save some time for this video, that is the proper solution for x, okay? Let's get to a more complicated question again. 3 to the power of x equals the 5th root of 9. So again, I've got to change that 9 to have a base 3. That's doable, right? Because I know that 3 squared equals 9. So if I just rewrite my 5th root bracket, and instead of a 9, I put a 3 squared. Okay? Now you might still be saying, okay, but what about that 5th root? Well, remember from a few lessons ago, we can convert a radical to an exponent. And all you got to do is shoot this 5 down below the 2. So you get 3 to the x is equal to 3 to the power of 2 over 5. Okay, everybody? So if you're left with a radical, right, you can turn that into just to have exponents. It's equivalent. 3 to the power of 2 over 5 is the same as the 5th root of 3 squared. It's the exact same. That number 5 just shoots down below the 2 in the denominator as the exponent. Now that we have the same base, set the exponents equal to each other. We don't even have to do any work here. it's already x equals 2 over 5. Okay, so a little bit of a trick there. Let's try another one. Now, what if you have a value in front here, like we have here? Well, we can actually remove that value. If we simply divide, as long as we do it to both sides of the equation, if we divide both sides by 4, just to remove it, right? So we're just basically reducing this equation. That's going to cross off. I get 4 over 4, which is just 1. And I'm going to have 256 over 4, which is 64. So I'm going to have 32 to the power of 2x minus 3 equals 64. Now, I don't have the same base there. Clearly, I have a 32 and a 64. So you have to think of a number, a common base that you can convert each of those into. Okay? Starting with 1. I mean, you can't do 1, so let's move to 2. Does 2 to the power of something equal 32? The answer is yes. 2 to the power of 5 equals 32. And 2 to the power of 6 equals 64. So I converted 32 to be 2 to the power of 5 because I know that that will give me a base of 2, and I know I can get a base of 2 on the other side if I do 2 to the power of 6. You at home, how are you going to figure that out? I mean, where do you start? I mean, you got to start at 2. And the more you use these numbers, the more familiar you'll get with them. You got to start with 2. I mean, I'm not going to ask you, if it were a test or assignment situation, I'm not going to ask you one that's too difficult to figure out. You know, it'll probably be like a 2, 3, or 4 kind of thing, right? And so you test it out. Now, we have the same base, but we have a power to power here that we have to multiply out so that I get a single power, okay? Then I can set the exponents equal to each other. So it becomes 2 to the power of 5 times 2x is 10x. 5 times negative 3 is negative 15. Now that I got rid of the power to power, now I can set the exponents equal to each other. Okay? So I've cleaned it up as much as possible. And now I can just say, okay, 10x minus 15 equals 6. Okay? 10x equals, bring the minus 15 over, becomes plus. X equals 21 divided by 10, which is 2.1, or 21 over 10. Okay? And that is our solution there. So our solution there is actually a decimal. Okay, so a 2.1 is our solution there. So let's recap what I did there. I didn't like having that 4 in the front of the 32. Okay, so I divided both sides. I divided it out so that I was only left with a base of 32 there. Okay, then I converted 32 to be 2 to the power of 5. I had to figure out a common base, right, for both sides so that then I can set the exponents equal to each other. So I did 2 to the power of 5 and 2 to the power of 6. Then I noticed that I had a power to power situation that I had to multiply out, and so I did that. So I ended up with 2 to the power of 10x minus 15 equals 2 to the power of 6. Okay, last question. This is the exact same as the previous one. I have a 3 in front of my base. Okay, so if I have a 3 in front of my base, I can divide it out on both sides to get rid of it. So if I divide this side by 3 and this side by 3, they cross off on this side, and I'm left with 9 to the power of x equals 1 over 3. Okay. Now, it looks like here you're probably wondering, what should my common base be? Well, my common base should be a 3 in my opinion. You can do 1 over 3, but I think a 3 would be good. I know that I can change 9 to the power of x to be 3 squared to the power of x. And I can change 1 over 3, because remember it's 1 over 3 to the 1. I can change it to 3 to the power of negative 1. So flip it so that the exponent then becomes negative. And now I have a base of 3 on both sides. I have 3 to the power of 2x equals 3 to the power of negative 1. Same base, just make the exponents equal to each other at this point. Okay? And your final answer is x equals negative 1 divided by 2, or negative 1/2. Okay? And again, you can do a left side equals right side check to double check your solution. Okay? So the big thing here is if you see a number in front of a bracket or your base, you've got to divide out that number to start. Okay? That's what you do. That's the big trick here. Once you do that, then try to figure out what the common base could be, right? If you're working with 1/3 or 3s and 9s, your common base should be a 3, okay? I converted 9 to 3 squared, and I converted 1 over 3 to be 3 to the negative 1. Then I had the same base, okay? And make note here, I had a power to power situation. I just multiplied those, 2 times x, which is 2x, okay? So these were all fairly straightforward examples, and the reason why they were straightforward was because we can find common bases between the two equations. You can't always find common bases, okay? That's just not possible. These questions were set up for us to be able to do that, but it's not always possible to find common bases. And when that happens, in our next lesson, we're going to learn a new way to handle those by using logarithms. Okay, so that concludes this section of solving exponential equations algebraically.